Hi, my name is Leonard Facchinetti, and let's write some code together, shall we? What we have on the menu today is the Fourier Transform. We are going to make it work. Hopefully. Maybe. We'll see. First things first. Isn't it weird how I transition from my starting soon screen to me? You see my OBS for like a split second? Isn't that weird? I don't know what that's about. Second weird thing, I updated to Monterey and now there is a little dot here when I'm recording my screen, or I guess in this case when I'm streaming my screen. Isn't that weird? That is weird. Weird stuff is happening. But let's talk about stuff that is not weird. Let's talk about Fourier transforms. Not yesterday, 2 days ago, we implemented the Fourier transform and it doesn't work. We'll figure it out. And to figure this out, I actually want to talk about the approach for fixing this. We had plenty of streams in which I'm debugging stuff. There is a method to the madness. And there is no right way of doing this. You can go from bottom up or from top down. The bottom up approach is you know the pieces of the puzzle. For instance, this stuff with imaginary numbers. We know the pieces of the puzzle. So we test these things first, and then we build our way up to the whole Fourier transform. Or we can do it from top down. We know the structure of the Fourier transform, so we can pretend that the pieces are working and we see if the structure is in place. And then we work our way down to these auxiliary functions with the imaginary number computation. When we were developing the Fourier transform 2 days ago, we went with a top-down approach. We started with the formulas, the big picture stuff, and then we implemented this lower level imaginary number situation. And as I said, there is no right way of doing. Some people will prescribe saying that you need to take one of the approaches, but I find that there is no right way of doing this. Sometimes you go top down, sometimes you go bottom up. 2 days ago, we went top down. Today I want to go bottom up. I want to see if the imaginary numbers computation is working right. Then we are going to test this rectangular to polar. It is just an auxiliary function that calls these two other auxiliary functions. We are going to write tests for all these things, and we are going to build our way up. Eventually, we will get the Fourier transform to work. Hopefully, maybe. We'll see. So, why am I deciding to go with a bottom-up approach? Why did I decide to go with a top-down approach 2 days ago, and I want to do it the other way around today? 2 days ago, I was trying to explain the high level of how a Fourier transform works, and I'm actually very happy with the explanation, and even though the implementation didn't actually work, I think it's a fine explanation of everything that is going on in the Fourier transform to build up intuition. So going from a bottom-up approach for this is how many mathematics books do, and I don't like that approach because it's hard to see the picture when I'm describing just one pixel in the picture. But now that we have this conceptual understanding, I think it's nicer for us to go from bottom up. We know what each piece is supposed to be doing. Let's test these things. So to begin with, the magnitude, that is supposed to be straightforward. Actually, we kind of already know that this is working just by eyeballing it, but it never hurts to have some tests because maybe by eyeballing the thing, I'm making some mistake. We already have this notion of unit tests, and we are just going to add more tests to this unit test suite. And that is going to come right after unit conversions. There. And maybe I'm going to split the screen this way, and I am fully aware that I'm in front of this part of the screen with the implementation. But the part that is more interesting is above. So let us write some tests for this. And I already wrote tests for many other auxiliary functions off stream. But I think it's nice to show the process. So that's why I'm doing it on stream. And also I didn't have the time to actually work on this off stream, because I also have life in the other 23 hours that I'm not streaming. Life is busy. Right, so magnitude. Well, if I can imagine the circle that is the trigonometric functions. It is laid out in this nice circle. So if the real is 1 and the imaginary is 0, the magnitude should be 1. That's an easy one to check. The magnitude of that number should be 1. So I'm going to check if it's not 1 and a bunch of other conditions. I'm going to add an error that reads imaginary magnitude, just like that. And let's start simple. Let's just run this test. To run this test, I have here a REAPER instance that is not outputting any audio. I muted, I lowered the volume, and then I removed all the hardware outputs. I really want to make sure that you are not going to hear this, because sometimes when you're developing audio effects, you make mistakes. And when you make mistakes, loud noises may happen. So just by loading this demonstration effect on the track, if I don't see anything on the screen, that means success. So this test is passing. Now let's do maybe the other 3 coordinates here. So we are going to check when you have, so I'm going to go from this point to this one, and then that, and finally that one. So this is real 1, imaginary 0. This is imaginary 1, real 0. This is real -1, imaginary 0. And this is -1, -1. They all, I think I'm going to format this. I try to avoid formatting these things because it's hard to maintain, but in this case, I think it looks nice. So these tests should be passing. And unfortunately, because of the way strings work in JS effects, if the tests don't pass, then the error will show up on the screen and it will keep showing up on the screen. So as a matter of habit, I am now always removing and re-adding the effect into the track. But when I do that, the tests run, and if I don't see anything, that means success. Here, I'll prove it to you. Suppose that I change this number to a 0. And then you see there is an error in the imaginary magnitude. But of course, that's not really an error. It was just me demonstrating the thing. So that is working. But let's compute another magnitude that is not so trivial. How about the magnitude at 45 degrees? Oh no, I have a good one. I have a good one to test. The magnitude is working with the... Yeah, is it like that? Yeah, I think it is like that. So the formula for calculating the magnitude is to calculate the distance, the Euclidean distance, the Manhattan distance. No, the Manhattan distance is something else. The Euclidean distance, I think. So if this side has a size of 2 and this size has a size of 3, then I know that this distance will be 5. Yeah, I'm pretty sure that that is the case. So 3 and 4 should be 5. Oh, no, I shouldn't be changing the last example. I should be adding to it. There you go. There you go. So nice. This one is working. Now let's work with the phase. This is actually more interesting. As I mentioned on Tuesday, there are plenty of edge cases that you have to consider when computing the phase. When some numbers are negative, you have to compensate for that, and this a10(2) function that comes with REAPER is supposed to do all this, but I haven't really checked. So let's check this by writing the tests. And this time, I think I'm going to start with this point in the circle because it should have a phase of 0 degrees. So phase is given in degrees and the number is in radians. So if I am on real 1, imaginary 0, I should be getting a phase of 0 radians. When that happens, this is the error. When that doesn't happen, that's the error message that should show up. Let's remove this and re-add. And it's passing. Now, I suppose that I should do all the 4 angles here, all the 4 points. So this is 0 degrees. This is, remember, this is in radians. So this is 90 degrees, but in radians it is 1/4 of a full turn, which is half pi. So the phase over at 0, 1, I'm going to put the spaces here because I know that I will want to format everything nicely the way I did it here. So this is pi over 2. Then -1, 0 is this third point, that is pi. And then this last point is -1, -1. And it's, that is not correct, is it? That is not -1, -1. That is -1, 0. So how come that is working? Oh, I made this right without realizing it? No, this is actually wrong. Let's go over this again with both things on the screen, the image as well as my coordinates here. So 1, 0 is this. This is 0, 1. That's correct. -1, 0. That's correct. And this is 0, -1. There you have it. And then over here on the phase, I should have the same inputs. 0, 1, -1, 0, and 0, -1. And that should be 3 times pi over 2. Let's see. 1, 0, 1, 0, 0, 1, 0, 1, -1, 0, and 0, -1. There you go. Let's run this test. Or maybe there is a nice way of writing this that will reveal the intention a little better, I think. So check this out. Doesn't that look nice? 0 quarter turns, 1 quarter turn, 2 quarter turns, and 3 quarter turns. The phase is wrong. Let's get into the effect and find which one is failing. Okay, that one is 0, so this one should... Oh, I am not showing you all what I'm doing, right? If I put this screen here, then that works. So I'm using Command K to peek, and this evaluates to 0, so that first one should be passing. That is passing. 0 means false, and false will not trigger the error. Now let's look at this one. Well, that is 1.57 blah blah blah, and what is this? That's 1.57 blah blah blah, so it seems correct to me. That is 0, so that is passing. It's not triggering the error. Now let's look at this one. Okay, so that is pi. We know this number, so let's check this out. Okay, that is 0, so probably, well, not probably, it must be the case that this last one is wrong. Yeah, so it seems like it wants to be negative, and that makes sense. We want the range of the phase to be from minus pi to pi. So we don't want 3/4 turns. We want minus 1/2 turn. Let me go over this in the image. So you can think of this as 3/4 turns, or you can think of this as 1 minus quarter turn. So the way that this works is, if you are above, then your phase is positive, and if you are below, your phase is negative. And in both cases, it goes from 0 to pi, and in the other direction from 0 to minus pi. Okay, let's save this, and this is not what I was expecting. Let me make sure that I saved the thing and remove and re-add everything. That looks better. The tests are passing. You can see that there are no errors. So now this should be okay. But I want to make absolutely sure that I'm following the document that we are actually using to implement this thing. I want to open this in Chrome, and there is this section on this chapter called polar nuisances, and these are the things that A tend to So we are using this REAPER function that calculates the arctangent of the division between these two numbers. And it's doing so in a way that is supposed to be smart and solve all of these issues. So we're going to go over the issues, and we are going to see if this is doing the thing it's supposed to. And we could implement this ourselves, but I actually expect people to use this function, though I don't really expect people to actually use the implementation of DFTs because it's gonna be slow. We are doing this mostly for the educational value. But these functions are actually useful. If you use REAPER's FFTs, the result is gonna come super fast, faster than our implementation. But the result is still going to be in the so-called rectangular form, and you still have to convert that to imaginary. And you still have to convert that to polar. So you're going to get coordinates in rectangular form, and you still have to convert that to polar form. So these functions are actually useful. And, therefore, I'm going to make this as fast as possible using A102 instead of rolling this out ourselves. But that said, I still want to verify that all the problems have been treated, and if not, then we'll do things ourselves. So first, radians versus degrees. And I think that we need some conversion functions for this, and we do have some unit conversion situation going on here. So let's just implement some conversion. I'm going to split the screen this way now. And let's implement a function called radian to degree, and another one called degree to bananas. How do you convert from one to the other? I think I know, but in any case, if I have the number in radians, I'm going to try to pull this off of my memory. I think the way you do it is you divide by pi and you multiply by 180. And I think that to go from degree to radian, you take the degree and you multiply by, no, you divide by 180 and you multiply by pi. Is there a better way of writing this down? Maybe there is. But whatever, let's just give this a try and see if I even got the formulas right in the first place. So let's write more tests. And this time we are writing tests for these conversion functions. Can I split the screen below? Thanks. So that's going to come before the imaginary numbers, right about here. And after dB to amplitude, there you go. So let's use this radian to degree situation. And I know that 0 radians is supposed to be 0 degrees. And that pi over 2 radians is supposed to be 90 degrees. Pi is supposed to be 180 degrees. Pi over 2 times 3, well, I guess I'm gonna do the thing that I was doing before, and I'm going to have a single formula to rule them all. Let me get rid of the body of all these function calls. And this is us doing everything from scratch, people. Everything from scratch. Pi over 2. So this is 0 quarter turns, 1 quarter turn, 2 quarter turns, also known as a half turn, 3 quarter turns. So that is 0, 90, 180, 2, 7. And then we are going to write something that looks like this. And oh, Bo is here. Hey, Bo. Great to have you. Welcome. And you are asking, what is that operator that looks like this? What does it do? This is called a logical OR. And what it does is, it's an operator. It's going to operate over these two operands. So let me go over what it actually does. I'll jump over to this editing tab. Let me make sure that I saved and that everything is syntactically correct. It seems to be. Remove, drop it there. Oh, and the tests are passing, great. So if I have, oh, well, first thing to know, in languages like C and JSFX, the EL2 language, 0 represents false and 1 represents true. Well, actually 0 represents false and any other number represents 2, but never mind that. 0 represents false, 1 represents true. So what is the result of false or false? I'll put the screen to the side so that you can actually see when I start peeking at values. So the result of false and false, false or false, is false. Now, if one of the things is true, then the result is true. And very importantly, when both things are true, the result is true as well. And I say that that's very important because usually when people say or in natural language, they're doing something like, do you want burger or pizza for dinner? In most cases, they mean either or, not both. So that is not the interpretation of this operand. The pipe here actually is doing or, but it's inclusive. So if both things are true, then the result is true. So that's this operator. That's what the operator does. But let me explain why I'm using it and what's going on these lines. The purpose of this is to do some sort of testing. So I have the implementations of the functions like these functions that we're coming up with, and I am doing some very basic tests. I'm just calling the function to see if I have the right result coming out. And the way that I do that is I call this, so I call the function with a certain value and I check, is it different from my expected value? If so, I'm going to add to this string, I'm going to just append to this string that is going to be shown on the screen for you to see the test results. And I may want to have multiple conditions. So I want to do multiple tests. I want to test at this position, I want to test at this position, and so forth. So what I'm doing is, I call the function, I'm checking, is it different from my expected value? If so, return that error. Or, and then remember it's an inclusive or, so, or if this thing is, so if this call does not output the expected value, return the error. So if any of these, or if all of these, or if some of these go wrong, we'll see the error. And then we have to jump into the console or jump into the IDE in REAPER, and we have to peek, as I did a couple minutes ago, and we peek and we find which failed, and then we fix it. So it's not awesome. And in theory, you could do all the tests with a single big OR expression. I could just OR this to that and OR the result to this. And have one big test. But I decided to go with like a test suite per function, more or less. I think it's a good compromise because if one function fails, then I can go see what is wrong with that function instead of just having to peek at everything and to see if to see what went wrong, which I mean, these functions are so basic that we'll probably never touch them again. But in bigger programs that we may want to refactor things, that can come in handy. In fact, I think I'm kind of already recreating stuff because I am changing to use this namespace notation with the underscore and everything. So in essence, I guess even the simpler functions I'm revisiting. So having these kinds of unit tests, I think will come in handy. That's why I have them. And that's what this operator is doing. Does that make sense? Right, okay, so these tests are passing because I actually jumped into REAPER to show you the OR operator. But I actually want to have one more test because I know for a fact that, let's try to do like 45 degrees. 45 degrees is half of a turn. Well, it's half of a quarter turn, I want to say. And that makes me happy. Oh, actually, I think I may want to do negative values on this function as well. I think they will just fall out. I don't have to do an extra work, but I do want to test this. So if I make all these values negative, then I expect all these values to be negative. Oh, I think I did one more than I should have. This one. Yeah, there you go. They all become negative, and I'm going to put one space here to line everything up, and one space there to line everything up. And I think that this will just work. So let's try this in REAPER. Silence means success. And Bo says, makes sense, smiley face. Awesome. I was expecting to see a column in that code. That is interesting. Well, typically you do condition and then question mark and then whatever you want to happen when that whatever you want to happen when that condition is true. And in most cases, in some cases, you may want to do something when that is not the case. So if there is an error, show the error. If there is no error, maybe we would have some success thing going on. But in this case, we don't have any success thing going on. We are just interested in the error condition. Silence means success. So in that case, we can omit. So in general, the form is condition, like this is a condition, question mark, then this is the then block, column, else, semicolon. But the truth of the matter is that this part is optional. It's usually written like this. So you may or may not include this part. It's actually optional. And I didn't know that before, so in our first streams with Arya, I said to him that he had to do something like this, where he explicitly says, I don't need to do anything here, so just no op, no operation. But then I learned that this was actually optional, so that's why we are writing it this way. And now let's drop this effect into the chain and run the tests. There you go, silence means success. Now let's write the opposite, the degree to radian. Well, that is easy to write because we can just swap the arguments. Should I have said degrees? We are saying samples and amplitudes. I think I should have said degrees. I'm going to rename this. Radians to degrees. And degrees to radians. And because I did that, of course, I need to do this with the argument as well. And then everywhere in there, we need to rename this. And of course, we need to swap these two. So I guess there is an advantage besides the aesthetics to doing everything in rectangular form like I was doing, because then I can just do this and it is supposed to just work. All right, let's drop this into the into the effects chain. And silence means success. So that takes care of nuisance 1, radians versus degrees. It is possible to express the phase in either degrees or radians, and it needs to go from minus pi to pi. Now let's save what we have, because we have been coding without saving or without committing for a while. Let's commit what we have. We have these new functions to convert stuff, and we have all of that, which is just testing the degrees to radians, radians to degrees, and then we are testing the magnitude and the phase, but we are not done with the test for the phase. Yeah, I'm going to leave here a to-do because I still want to test more phases, making sure that all the nuisances have been taken care of. Right. Bo says, and I say that back to you, Bo. Let's look at nuisance 2, divide by 0 error. That will happen when I have, so the arc10 thing is dividing imaginary and real. So if my real is 0, that may be an issue. what is the right answer in this case? The right answer is that the angle, the phase, is exactly 90 or minus 90. So if my real is 0, then my angle here is either exactly 90 or exactly minus 90. And we have a test for that already. This phase test with a real of 0, but this is an imaginary of 1 and an imaginary of minus 1. And in both cases, it's getting it right, either 90 or minus 90. So nuisance number 2 in the bag. Number 3. So this situation is when you have a negative real. Minus 1 in this case. If you're negative, oh, and I guess in your imaginary as well. So if you have a minus 1 situation going on, then minus 1 is over there. So the angle should be minus 135 degrees. That is because there is minus 90 up to here and then minus 45 up to there. So 90 plus 45, 135. There you go. So let's actually add a test for this. We don't have one right now. And then let's put a minus 1. We expect to see minus 1.5 quarter turns. This pi over 2 that keeps happening here, pi over 2 is 1 quarter turn. So we expect to see how many quarter turns? 1.5 in the negative direction. Minus 1.5 times pi over 2. That is working. So REAPER seems to have taken care of all of this. Great. But it is good that we are reading this over, we are understanding the problem, and we are adding tests for these things. Now, I will take a step back and think about whether you would actually want to write these tests or not. Typically, the wisdom is that you don't test the libraries that you are working with. So if you are using JS effects, you don't test the implementation of FFTs, you don't test the implementation of sine. And if you're, this wisdom comes from like web frameworks. So if you're using Ruby on Rails, you don't test Ruby on Rails. You write your tests for your application, not for the framework. Now, in this case, it could be argued that I'm kind of writing the tests for the framework because I'm more or less relying on this A10 function and it's doing everything for me. But I think there is still value in writing these tests. First, to verify that it's doing everything as we expect it to. But second, because there is a difference in meaning here. This is calculating the tangent of these two, the result of dividing these two numbers, imaginary divided by real. And that's great. But this is like calculating the arc tangent of the result of a division. While in our function, we are computing the phase. And of course, they implemented A10 too because it's useful for this operation. But now we are giving it a name, and the meaning is super important here. So I think there is still value in writing the tests that we are writing. And in many cases, I would just write the tests, verify that everything is correct, and then throw them away. But in this case, I think I'm even keeping the tests. I just think it makes more sense that way. Okay, now let's talk about the phase with a very small magnitude. Well, this is not something that we can do much about in our implementation. The problem is that you can see it in this figure. If the magnitude is super small, then essentially it's noise. And this computation is not really meaningful. It's not the case that the phase is going all over the place here. It's just the case that the numbers are very small. They're mostly noise. You can think of them as like very small random numbers, and then they're dividing two very small random numbers, and you're calculating the arctangent, and you're gonna get something crazy. Now, we could try to do something about this by maybe checking if the number is very small and then not doing anything and just returning a phase of 0. But I think it is more fair to actually just return the noise. And it is also faster. We don't have to do any other checks in this, which will make things faster. There is one thing to be said. This function call is just essentially this function call, and it does introduce a little bit of overhead. It makes everything just a little bit slower because function calls are not free, as we learned in our previous stream in which we were benchmarking this stuff. We were measuring the performance. So there is an overhead here, but I think it's meaningful and nice because we have the arguments in the right order, real and imaginary, as opposed to this, and it says what it's doing out loud, and the overhead is small. So maybe adding a check for small numbers here, maybe not advantageous, but having this function call, I think, is advantageous. So there you have it. That's the discussion of how and why I do the things that I do in this world. Nuisance 5, pi to ambiguity of phase. Now the issue is that 2 pi is at this position. So is it positive 2 pi or negative 2 pi? And I don't think that there is anything we can do about this. Well, there is something we can do about this. The issue is here that we don't know if it's plus or minus 2 pi. But it compounds because suppose that there is some signal that is just rotating in terms of phase, just going like this around the circle in terms of phase, which is something that a signal may do. And then if that happens, the plot of this signal is going to be this wrapped thing here. It looks like that. But really the phase of the thing is this thing. I mean, they amount to the same because what am I saying? I said that 2 pi is over here. No, 2 pi is over there. That's the issue. 2 pi is over here. And the issue is that maybe this angle, let's say, we actually have an example of this. So we ran into this issue before. We said that this angle here was 270. It was 270. But then we learned that no, we need to represent this in the range between minus pi and pi, so this number needs to be minus a quarter pi. But then the issue becomes your graph kind of looks like this, which in many cases makes sense to actually represent this because if the person reading the graph knows what they're doing, they will know that this graph actually means this unwrapped thing, the phase is just going around the circle, and this takes less space. So that makes sense, actually, to represent it like this. But then the issue is, this angle can be represented as 270, as minus 90, as 360 plus 270, 630. So this is also 630, and it is actually an infinite amount of angles, right? It's all these ones that I mentioned and all the other ones you can imagine yourself just by adding 360 over and over to the value. So we are only going to output numbers between minus pi and pi, but we could have, maybe I will add this to the list of things to do. We could have some auxiliary functions to unwrap the phase. And actually this algorithm is implemented over here, but what this does is it takes a graph that looks like this and unwraps it and shows it like this, which in some cases may be advantageous. So maybe we will want to have some sort of spectral analyzer that is capable of unwrapping the phase. whatever. So for now, we are not going to deal with the ambiguity of the phase. We are only going to deal with the magnitude is always positive, the pi ambiguity of the phase. So that's the one that I was thinking about. So the pi ambiguity of the phase is pi is over there. And yeah, the issue is that if your signal has a rectangular representation that looks like this, the magnitude is always positive. You cannot have negative magnitudes, but you can have negative real values. So your phase just keeps jumping up and down. Well, actually what's happening is that the phase is... This is not noise. No, it actually is noise. Random noise can cause the phase to oscillate between pi and minus pi. So when we are here, is this pi or minus pi? That's the question. And it kind of oscillates given to because of noise. It oscillates back and forth. And it's annoying that the phase kind of looks like this. It is going up and down, which is already an issue. But even if it was just stable here at pi, then it would be kind of annoying to see the phase just going from 0 to pi, back and forth. The phase is not all over the place. It's just that the phase needs to be plotted that way. You need to think about the phase that way so that the magnitude is always positive. You can see that the values that go below 0 are the ones that are causing problems in this graph. But again, I don't think there is anything we can do about this in our implementation. I don't think there is even any tests that we have to write for this. Well, we could, I guess, implement something that allows the magnitude to be negative, but I don't want to get there. Yeah, and we would have to call that something else. Maybe unwrapped magnitude. Right? If you allow the magnitude to go negative, then you can leave the phase alone. It can be 0 at all times, which is more truthful. If the thing that you care about is the phase being 0 at all times, is more truthful to the original signal, as indicated by this imaginary part being stable at 0. And then the final issue is spikes between pi and minus pi, which is this figure that we already looked at. There is nothing we can do about this. Maybe we could have something that would smooth out this noise by looking at small values, as I mentioned before. We could check if real is less than a very small value, then just return 0. But I don't think I want to do that. I think I will leave that to you as the user of this. So I will give you the phase as truthfully as I can. Maybe, yeah, I guess I will have a node to do this. So it's the same way that I can unwrap the phase, I can reduce noise in phase calculus. So maybe I'll have a section here about phase, and that says unwrap and reduce noise by checking small values and returning 0. All right, we went over all the nuisances. They have all been taken care of. Let's finish off this test by just removing the to-do. Now let me take a step back because I actually forget why I was doing this whole endeavor. Oh, so we already have tests for these functions and they just came as freebies because I was reading the nuisance about the radians and degrees situation. So I decided to write the converter and I also wrote the tests. Then for the imaginary numbers, we tested the magnitude and phase and we can trust that they work. Let's move on to the rectangular to polar. Well, what's going on here is we have the result of computing the DFT, and the result of computing the DFT is going to be in terms of reals and imaginaries. and we want to call these functions for all of them. And then I wrote this auxiliary function to do that. It is just mapping over the real and imaginary parts and calling the auxiliary functions. And I'm not even sure if this kind of belongs here or if it belongs in the DFT. I was kind of going back and forth because this has to do with imaginary numbers, but it is so useful in the context of DFTs. I guess I'll keep it here, but I will change some things about this implementation. I'm not happy about this implementation. I'm not happy about the data structures in there, actually, because here I'm using arrays. In the computation of the DFT, I was using circular buffers, not in the implementation of DFTs, no. In the implementation of the line graph, I'm using circular buffers. So I cannot easily just plot the reals and imaginaries. And I think I remember doing that. I don't think, I know. I copy and pasted the implementation of the line graphing thing, but that's not even working. So I think it's time to actually do this right. And what we are going to do is to change the implementation of something so it makes more sense. What are we going to change the implementation of? Now that's the question. I can change the implementation of this so it works over circular buffers, or I can change the implementation of the line graph situation so that it doesn't work over buffers, it works over arrays as well. And I have a preference. If you're watching me and you have a preference, then let me know. But I think I have a preference. And it goes like this. I think that we should implement the line graphing thing in terms of arrays. First, because it will make everything here easier. Second, I think it makes more sense to have the array as the primitive. I think it makes more sense on the context of the line graphing thing. I'm going to move the screen there so you can see what I'm talking about. So the data that is coming into the thing that draws data on the screen, this data is a circular buffer. And I think that using circular buffers here may make everything slower. And there is an even more interesting fine point that I want to make. So as an example of how we are using the line graph here in this demonstration, we have a delay line. So we are doing sort of an oscilloscope. We have a delay line, and as a sample comes in, we put the sample in the delay line. Where is it? This. Am I right? Yes. Delay line, circular buffer push. So we put stuff in the circular buffer in the sample block, but we show it on the GFX block over here. And the issue is that these two blocks, the sample block and the GFX block, run simultaneously, concurrently, in parallel. So it may be the case that I'm writing over here and I'm reading over there, and I'm making things out of sync in the process. So that's another issue with using circular buffers. Now, of course, circular buffers were the natural choice when we started, but I think that the right way of doing this is you just push stuff into the circular buffer, then you have an auxiliary function to convert from the circular buffer into an array, and then you plot the array. But this auxiliary function is going to copy things over, and there is this Mem Copy function, comes with JS effects, that we can use to I suppose it's fast, I hope it's fast, to very fast copy blocks of memory around. And I think it's fast enough for this purpose of the GFX block. So we are going to copy from the delay line, we are going to produce an array, and then we actually graph the array. That will make many things simpler, including graphing the result of the magnitudes and phases, because they are going to be arrays to begin with. So what we have up next is to convert So maybe I will write this down. A circular buffer to array converter. Then change the implementation of graphs to use to use arrays. And we may even have a higher level function that is going to just put the two functions together. The function that is going to do this conversion, and then the function that does the graphing using arrays, so that you can pretend that you have a function that graphs a circular buffer for you, if you so wish. Whatever. That's just an auxiliary function that is sugarcoating the situation. That's what this is about. And in fact, I think it's time for me to wrap up. So now you know what I am going to do tomorrow. I'm going to work on this part, and we are going to keep building our way up from bottom up, trying to fix whatever is wrong with our DFT, our Fourier transform. And maybe it's even right, it's just plotting wrong, whatever. We'll figure it out, but we are going to do this very slowly. We are going to do this thing first, and then we are going to use that thing to plot the reals, imaginaries, magnitudes, and phases. Maybe not the reals and imaginaries, because this book that we are following keeps telling you that don't try to make sense of real and imaginary. Just look at magnitude and phase. Real and imaginary is for computation, it's for computers. Magnitude and phases are for humans. So we are going to work on this conversion thing, and we're going to keep building our way up. We're building solid foundation here, I think. So thank you all for being here. Thank you both for being active on the chat. Thank you everyone else who is watching this later, and people who support me on PayPal and Patreon. You're the best. I see you tomorrow, and we are going to tackle these tasks. Bye. Have a good one.